All right, guys, what we're going to be talking about here is an idea that when you think about it at first, it's not real hard. And then as you think about it a little bit more, you're like, oh, okay, maybe I don't understand it quite as well. But this is an idea that's actually very important for a lot of other things that we talk about as we get further into this class and the basis for some things in the future that are important. Okay, so again, the idea is not that bad, and you'll see what I'm talking about as we get into it. But what we're talking about are what are known as improper integrals. Now, when you look at this integral right here, you're looking at it at first like, okay, I know how to do this. Like if I was doing this by hand, I would take the antiderivative of this function by making it 1, and we've got that infinity, and you're like, and you're like, okay, you look at this initially, you're like, okay, I would know how to do this, but this infinity right here is a problem. Now, the other issue that we have here is if I were to look at this graph, so if I was looking at the integral from 1 to x squared, technically, this graph looks like this, and the graph in either direction gets closer and closer and closer to the x-axis. Well, if I was to go from 1 to infinity, initially most people look at this and they're like, okay, well, to me, that looks like there's an infinite amount of area. Because this graph never touches the x-axis, you look at that and you're like, oh, I can see that there's just going to be more area and more area and more area, because if I'm going to x, as x goes to infinity, way out in this direction, then that's saying there's never going to be an end to the area that is being generated. So that would be what my answer is, and we would just basically say that this does not exist. Okay? Before we get into what's going on there, we do need to say that this is what is known as an improper integral. Now, an improper integral, all that means is I have infinity at either the top or the bottom of my integral sign. Okay, it's one of my limits. Now, we talked about this briefly before when we were talking about the fundamental theorem of calculus, but one thing that's very important to understand about an integral is it does have to go from one specific number to another specific number. And so on the AP exam, and this idea, I'm only going to talk about it right here, and then when we start reviewing for the test again, we'll discuss it more. But in order to properly use terminology on these problems, what we do is we say the limit as b approaches infinity if we're talking about the top number, or if you were talking about the bottom number, the limit as a approaches negative infinity. All you're basically doing is saying, okay, we're getting really close to infinity, but that means because we're getting close to infinity but not actually getting there, we're actually to a number. Now, that's very confusing, and quite honestly, it's more terminology than anything else. Saying, okay, I'm just getting way out there and I'm trying to find the area. Can you help me do that? Okay. Before we go any further as well and show you how that works, when we look at these problems, this is where you'll have to think about this and you'll be like, well, wait a minute, does that make all the way sense? There are a couple terms that we have to talk about. The first term that we need to talk about, and we talk about them together, is whether or not this particular integral converges or diverges. When we say that an integral converges, that means that there is a way to find that actual area. And when you find out what that area is, it's equal to a specific number. And I know that seems kind of counterintuitive based on what we talked about at the first, saying there's always going to be more area, and we'll discuss that a little bit more in just a second. If we get that this particular improper integral is not equal to a specific number, in other words, when I try and evaluate it, I get infinity or negative infinity, that just means that there's too much area to actually find. Now, I know, again, this idea seems kind of weird because you're probably saying, what does that mean to have too much area? Why? How can there be enough area that we can count it? Sometimes when we look at something else, then we don't have enough area. So here's kind of the way I like to look at it to understand what's going on. If I were to actually evaluate this integral, just pretending like his infinity is there, technically, again, we would write this as the limit as b approaches infinity from 1 to b of 1 over x dx. And it doesn't really matter if you do that or not. Most of the time, these problems show up on the non-calculator portion, or excuse me, on the non-free response portion, so it's like multiple choice. So when you're worrying about it on the test, I don't worry about it a ton. But if I were to carry this out, take the antiderivative, then we're able to plug in 1, 2, and infinity. I'd have the ln of the absolute value of infinity minus the ln of 1. Now, the ln of 1 is 0, but the ln of any number as it gets very large is still a very large number. So I've got infinity minus 0, which is equal to infinity. Now, what that means in this example, because if I were to look at this graph, it would look like this. The problem here is, again, I can see that it's infinity, because if I'm going from 1 to infinity, this area right here will be infinity. I just evaluated it using the second part of the fundamental theorem of calculus. What's really happening here, and this sounds kind of weird, but what's happening is this graph is not getting close enough to the x-axis fast enough for us to say, I don't need to count that area anymore. And we will actually look at this idea a little bit later when we're talking about what's called a series, where we can kind of prove why this is happening. But for right now, don't worry too much about it. Just know if you evaluate the integral and this is what you get infinity, we would say that this particular improper integral is divergent. Okay? So now if I was to look at this one, we go back to our original equation that we were looking at. I would make this x to the negative 2. I take the antiderivative of that, and I get negative 1 over x, because it's x to the negative 1 divided by negative 1, and then I just kind of evaluate it from there. Well, if I look at this one, I plug in infinity and 1, I get negative 1 divided by infinity minus negative 1 divided by 1. This first part, I'm dividing by a massively huge number, so that becomes 0. Minus negative 1, that's the same as plus 1. 0 plus 1 is 1. That means that this particular improper integral is convergent, and it's convergent on 1. I found out, I can tell that it's convergent immediately. Now, this idea of convergence or divergence is very, very important, like I said earlier. Knowing what the integral is equal to is important, but more important is understanding the idea that I can tell, and again, what's happening here, if I look at the graph, I've got this graph, and just the way that this graph decreases, if you will, it gets closer and closer to the x-axis fast enough that eventually, way out here, the graph is so close to the x-axis that I just don't count the area anymore. Now, don't think about either of these ideas too much, because quite honestly, you'll start being like, what in the world? How does one give me area, and the other one, there's too much area to count? I honestly would tell you, don't worry about it too much. So there is actually an easy way, just by looking at the integral, to tell whether or not it's going to be convergent or divergent. What we do is we look, almost all of them, when we look at the improper integral from like a to infinity, we're going to have 1 divided by x raised to some n power. If n is less than 1, then automatically we can say that that integral is going to be divergent. If n is less than or equal to 1, If n is greater than 1, then automatically I can tell that that particular improper integral is going to be convergent. And I don't need to take the antiderivative to tell what it is. I can, and I can tell what that's going to be, but automatically I can look at it just by knowing what power x is being raised to on the bottom. Okay? And we're actually going to skip vertical asymptotes. Basically what's happening on 1 over x squared is I get really, really close to at x equals 0. And basically, and I will talk about this real fast, if I have a vertical asymptote and I'm getting really, really close to that, and I'm trying to determine whether, like let's say I was doing the integral from 0 to 1 of 1 over x squared. What we do in this case is we basically look exactly the opposite. So when I look at this particular function, and I say, okay, I know if that went to infinity, that would be convergent. But as I get really, really close to a vertical asymptote, the exact opposite is true. That's simply not going to get there fast enough, so I would say that this one is divergent. And I wouldn't worry about vertical asymptotes too much, and you can evaluate it a little if you want to try, but honestly, I wouldn't worry about it too much, okay? So here's one real quick. Now I look at this, and this is 1 over x to the 1/2 power. I can see right away that that power is less than 1, so if I were going to infinity, this would be divergent. But because I'm going from 0 to 1, and I've got myself an asymptote at x equals 0, I could say that this is convergent because that power is less than 1. So all I would do now is I'd move that x up to the top. I get x to the negative 1/2. And then I would take the antiderivative of that. So I get x to the positive 1/2 divided by 1/2, which is the same as multiplying by 2. And we do the integral from 0 to 1. So I get 2 times 1 to the 1/2 minus 2 times 0 to the 1/2. 1 to the 1/2 is 1 times 2 is 2. So I would find out that that area is 2. Again, this graph would kind of look something like this. Okay? And I would just be finding this area. And because that power is less than 1, I can now say the exact opposite is true. I can tell that that's convergent. One other thing that we can do is if I'm looking at if I was looking at this particular function right here. Now this one's way more difficult to try and integrate. We don't have techniques to do that. But I know if I wanted to know whether this was convergent or divergent, all I would have to say is, wait a minute, I've got x squared right there. I could compare this to this function right here because I know that power right there is less than 1. Because this particular integral is convergent, so too will this one be. Now that doesn't mean we know exactly what this integral will be equal to, but I can say that this function is going to be, or this integral, excuse me, is going to be convergent due to the fact that I know that this series, or excuse me, this integral is already convergent as well. Okay? Here's another one, the integral from 1 to infinity of 1 over e to the negative x squared. If I move that down to the bottom, I've got 1 over e to the x squared. We'll talk about this more, but exponential functions actually grow faster than polynomial functions. So if I've got e to the x squared, I could actually compare that to 1 over e to the x. I know that that is convergent. So I could say that this one is going to be convergent as well. And we'll talk more about that later. But just know anytime you have an exponential function, it's going to be convergent if the exponent part is on the bottom. Okay? Now, one last one that we do need to talk about is what happens if we have sine of x on the top. What we have to realize with the sine of x is the sine of x graph always goes between -1 and +1. So basically, I've got 1. At its biggest, I've got 1 over x squared. So if I wanted to know if this was convergent or not, I could just compare it to 1 over x squared, and I would find out, because that is convergent from 1 to infinity, that this integral will be convergent as well, just due to the fact that the sine of x never gets bigger than 1, so I don't have to worry about it. Okay? Now, one like this, what we have to be a little bit careful on this one, just because when I look at this, I'm like, okay, I've got x squared on the bottom, but I'm taking the square root of that. When I take when I get out at infinity, this minus 0.1 isn't going to matter. So what I really have is the square root of x squared. Those two would cancel each other out. So if I wanted to, I could compare this particular improper integral to 1 over x, and they would behave exactly the same way. We talked about this already, but that is x being raised to the first power. That is divergent, so I would know that this particular improper integral is divergent as well. Now, this idea of convergence and divergence, again, you can show what's happening pretty easily. Wrapping your head around what's happening and understanding why some of these you can find a value and some of them you cannot is something that you need to think a little bit more about. It is a little bit more complicated. If you have any questions about this, please let me know.